Alright, so now that we've seen how we can name some of the simpler alkanes, I want to kind of try to branch out a little bit more and look at alkanes that are not quite as linear as the ones that I've shown you before. Okay, so if we were to look at butane, okay, we said butane had the chemical formula C4H10, okay, and the structure that I drew for this had the 4 carbon atoms all in a line. Okay, and we said that each carbon was going to be fully saturated with bonds, so we can draw in all these hydrogens here. Okay, now it turns out that this is not the only structure we could draw that has 4 carbons and 10 hydrogens. Okay, so for example, instead of having 4 carbons in a row, we could have had 3 carbons in a row, with 1 carbon coming off of the middle carbon of that chain. Okay, and just like before, we can go through here and we can add in all the hydrogens. Okay, except for this case, this carbon right here only gets 1 hydrogen because it's bound to 3 carbons. Okay, so we fill all these in. And real quickly, here we can count that we have 1, 2, 3, 4 carbons. And we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. So this is also C4H10. And this is the reason why we can't get away with just naming these things by their chemical formulas. Okay, we say that these two things are constitutional isomers of one another, which means that they have the same chemical formula, but different connectivity. Now, as you can imagine, as the molecules get bigger, the number of constitutional isomers can increase. And before I do that, though, I just want to show you that there's another way of expressing these molecules which will allow us to do this much quicker. So for example, for the C4H10 molecule on the left-hand side, where we have all 4 carbons in a row, the way that we can represent this is as follows. Okay, and you can see here that I've drawn a zigzag. Okay, and the endpoints are assumed to be occupied by carbon atoms, as well as every vertex. Okay, so we have the 2 vertices and the 2 endpoints. That gives us a total of 4 carbons, and this shows us how they're actually connected. Now we assume that each carbon is going to have its full complement of hydrogens. Okay, what that means is we look at the number of bonds that a carbon has that are explicit in the drawing. So for example, this first carbon here is attached to the second carbon. Okay, and since it has 1 bond to that carbon and nothing else showing, that means there must be 3 other bonds because carbon can form 3 other bonds for a total of 4. So that's assumed to be 3 hydrogens. Okay, so we don't draw it, but we just remember that they're there. Carbon 2 here has an explicit bond to carbon 1 and to carbon 3. Okay, so that's 2 bonds that are showing, but because carbon can have a total of 4 bonds, there must be 2 that are not showing. And that would be these 2 here. And again, we don't draw them out, we just say that they are implied to be there. Okay, this is what we call a line drawing. Okay, so that's the line drawing for the first isomer of butane that I showed you. The line drawing for the second isomer would look like this. Okay, again, we have every vertex and every endpoint counting as a carbon atom. Okay, so those are the 4 carbons, and we assume that each of the carbons has as many hydrogens as could possibly have in order for it to have a total of 4 bonds. So this carbon right here that's on the left-hand side is only showing 1 bond to carbon, so there must be 3 others, and we're going to assume them to all be bonds to hydrogen. Okay, this makes life so much easier when we're trying to draw these molecules. Okay, so let's look at some other isomers now that we have a faster way of drawing things. So if I were to ask you to draw all the possible constitutional isomers of C6H14, okay, here's how you would do that. You would first start off by drawing the straight chain one. Okay, so we call this unbranched. Okay, every carbon is just kind of going in a straight line. In other words, the way that they're connected is one carbon to the next and to the next. There's no one carbon that shoots off in a different direction. Okay, so this is 6 carbons. And if you want, you can count them up. There's 14 hydrogens there. Okay, another possible isomer would be if I took off one of those carbons at the end and put it maybe right here in the middle. Okay, so now we have a branch, or I could have put it on the second carbon. Now, you might try to draw something like this and say that that's a different isomer. But remember, we're just looking at the molecule from one side here. These two are actually the same. Okay, so these are not 2 different isomers, they're just 2 different views of the same molecule. Okay, another possibility would be something like this. Okay, of course, we could have something like this, and I think that might be all of them. I'm trying to see here if there's any that I'm missing. And no, I believe that I have them all here. Okay, so these are all the different isomers. Now here's the thing. How do we name these? I mean, we said that this guy right here is hexane. Okay, but this has the same chemical formula. This has the same chemical formula, as does this, as does this. We can't call them all hexane. Okay, because these are different molecules with different properties, different structures, and each compound has to have its own distinct name. And that's what we're going to look at in the next video.